So now that we know how to determine if something's a solution, the next question would be, how do we actually find a solution? Well, let's think about this. Let's start with the linear system. 4x1 minus 4x2 plus 4x3 is equal to negative 4. 4x1 plus x2 minus 2x3 is equal to 5. And then minus 3x1 minus 3x2 minus 4x3 is equal to minus 16. So our question is, how do we solve this? So you might know how to solve this using a method known as the addition method or the elimination method. They both mean the same thing, they just have different names. And so in that method, there's actually 3 things you can do. So one thing you can do would be to multiply an equation by a number. Another thing you could do would be to add up 2 equations. And the third thing is a little bit trickier, but it's basically just that we can switch the order of equations. It doesn't matter which one came first, which one came second, or which one came third. You can switch the order as much as you need to. So, to simplify this process, we're going to use matrices. And I'm going to do 2 matrices in particular. The first one is called the coefficient matrix. So a matrix is just a rectangular array of numbers. We typically denote it using square brackets. So coefficient matrix might give you a clue that we're going to use the coefficients, and we are. Every row of this matrix is going to correspond to an equation. So I have 4x1 minus 4x2 plus 4x3. And those are all the coefficients of the first equation. The second equation has a 4, a 1, and a negative 2. The third equation, minus 3, minus 3, minus 4. So every row corresponds to an equation, and every column corresponds to a variable. You'll notice the first column is all the coefficients of x1. The second column is all the coefficients of x2. And the third column is all the coefficients of x3. So that's the coefficient matrix. And while that is helpful, that's usually not the one we use. Instead, we use the augmented matrix. So the augmented matrix is going to be very similar to the coefficient matrix. In fact, it's going to start with the coefficient matrix. 4 minus 4, 4, 4, 1, minus 2, minus 3, minus 3, minus 4. Next, we draw a vertical bar. So the vertical bar is going to indicate our equal sign in our system of equations. And then we write the constants. Negative 4, 5, and negative 16. So this is the augmented matrix. So how is this helpful? Well, it's going to be very helpful. We're going to use this, and we're going to do what's called row operations. So row operations are just valid things that we could do to solve equations. And there are 3 of them. So when I talked about solving using the addition method or the elimination method, the first thing I said you could do was to multiply an equation by a number. So here we can multiply a row by a number. So we multiply a row by a number. Second thing we could do, I said we could add two equations together. Well, we're changing that slightly, just the wording, when we're dealing with matrices. We can add a multiple of a row to another row. And the third thing we can do, like I said, the order we wrote down the equations doesn't matter. So we can interchange two rows. So these are the three things we can do. So the question might be, why would we want to do these? And how do we know what to do? Well, my ultimate goal for this system of equations is going to be to use these row operations to turn the augmented matrix into something that looks like this, where A, B, and C are going to be some number. So if I do this, I now have x1 plus 0 is equal to A. 0 plus x2 plus 0 is equal to B. And then 0 plus x3 is equal to C. So I have my solution, A, B, C. So this is my ultimate goal during this process, is to turn the matrix into this. So we say a matrix is in row echelon form if all of the following hold. All non-zero rows are above any zero rows. And a non-zero row is just a row in which at least one entry is not zero. 2, the first non-zero entry in each row is in a column to the right of the first non-zero entry in the row above it. And this is known as the leading entry. It's also known as the pivot. And 3, all entries in a column below a leading entry are 0. So before I continue this definition, I'm going to give an example. So here's a matrix with 3 rows and 4 columns. And this one is going to be in row echelon form. So the first thing says that all non-zero rows are above any zero rows. I don't have any zero rows here, so I don't need to worry about the first one. Number 2, the first non-zero entry in each row is in a column to the right of the first non-zero entry in the row above it. So basically what that's saying is, here I have a 3. If I move down and right, I have a 4. And if I move down and right, I have a 2. So as I'm looking at the first thing that's not a 0, I should be moving down and to the right. 3, all entries in a column below a leading entry are 0. So the leading entry of the first row is a 3. Everything below it is a 0. The leading entry in the second row is a 4, and everything below it is a 0. The leading entry in the third row is a 2, and there's nothing below it that needs to be a 0. So to continue the definition, we say a matrix is in reduced row echelon form if in addition to the above requirements, the following are also satisfied. The first non-zero entry in each row is a 1, and all entries in a column above a leading entry are 0. So let's do an example of that. So 1, 3, 0, 0, 0, 1, and 0, 0, 0. So the first thing to note is my row of zeros is at the bottom. That's what number 1 is saying. Number 2 is saying these leading entries should move down and to the right, which they do. 3, all entries in a column below a leading entry are 0. Here's my leading entry in the first row. Everything below it is a 0. My leading entry in the second row, everything below it is a 0. If you notice, the first non-zero entry of each row is a 1. And also 5. All entries in a column above a leading entry are 0. So here's the first one. There's nothing above it. My second row has zeros above it.